Hi, welcome to StatStuff. I'm Matt Hansen. In this lesson, I'll show you how data can change over time. The variation in the variation affects how we measure our data over a short or long period of time. Therefore, it's critical that we understand if our data is short-term or long-term, because it could make a difference in how we find and account for the process variation that we're trying to minimize. Once again, this lesson is building on our previous topics on variation, so it may be helpful to review those ahead of time. But for now, let's begin by exploring how variation can impact the time frame of our data.
The time frame for the collected data can significantly affect the analysis results that we're expecting from our data. So what would happen if your data only included samples that might have been for just one day, or maybe only weekdays in a 7-day-a-week process, or maybe only one shift when you have 3 shifts available over a 24-hour-day process? Well, obviously, if you're only collecting days for those different types of periods of time, you're excluding something and you're introducing some bias in your data. So the implications from that could be very obvious. But what about when it's not so obvious? How do you know what's a reasonable time frame to include in your data? Before you can answer that, you got to first understand basically 2 types of variation in process that we had covered in a different lesson. So we talked about how there is common cause variation as well as special cause variation. As a quick review of those things, we would say that common cause variation is the natural or random type of events that would occur within a process, and these would normally create a normal distribution. And these are things that are occurring from within the process. It's part of the design, or maybe just normal wear and tear and breakdown, or some environmental issues on a general basis that seem to reflect the process itself. This is all common cause type of variation we might see. Special cause variation, though, is something that's not normal. That is, it's unnatural or it's erratic, and it would create a non-normal distribution. There's some sort of anomaly or bias that might be introduced here. It's something that occurs from outside of the process, typically like a power surge or extreme weather conditions, or something like a poor batch of raw materials that were received. Again, it's not normal or not typical. So in understanding that will help us understand the foundation for the type of data that we're going to be collecting. So first we can collect short-term data. Short-term data is data that's collected from subgroups within a process, and typically you're only going to see common cause variation within short-term data, not much, if any, special cause variation. And the data will typically also reflect a snapshot in time. And we compare that to long-term type of data. Long-term data is something that's collected across multiple subgroups or all the subgroups, and it's going to be capturing not only the common cause variation but also special cause variations within it. And the data itself is going to reflect a much fuller range of time.
Now let's see an illustration of the impact of variation over time.
Well, processes will tend to show more variation in the long term than they will in the short term. So long-term variation is made up of both short-term variation as well as process drift. Now the shift between long and short-term data can be measured by taking samples of both the short and long-term data. The shift of short-term processes over a long term is about a 1.5 standard deviations on the average that we would see. And this is more often used when we're measuring process capability, and we're going to get a lot more into that when we get into the analyze phase and exploring some of that process capability. But for now, it's a good introduction just to know that normally the short-term drift that you would see within a long-term set of data represents about a 1.5 standard deviation drift. So just to show an illustration of this, let's say that we have this time frame of January through August, and let's just say for argument's sake that represents a long period of time. Let's say we collected data over that long period, and the data representing that long period of time is what we're calling our long-term data. Now the average for that would fall somewhere in the middle. This is where average or central tendency would fall, like a true mean over that full extended period of time. Now this would be the long term over that extended period of time. Where for the short term, we might collect our data and it might look something like this, where the average is actually going to be shifted a little bit to the left. We might do another data collection for another short term, and again this data might be shifted a little bit to the right. We keep doing additional collections of data, and we'll see that it doesn't exactly represent the long term because there's lots of other things going on within the data itself. Again, there's some special causes that might be causing it to shift in one way or another away from that true mean over the entire time. But each of those at least have their own common cause variation within each set. So over the long period of time, if we collected the short-term data, we'll see some kind of movement like that. And that movement will represent the drift, where the short-term data is somehow drifting back and forth across the true mean over time. That's what we're saying, that drift or that shifting that we're seeing between the short-term data represents about a 1.5 sigma or 1.5 standard deviations on the average. So what time frame should we be using based off of all this? Well, it depends on the type of data that you're measuring and the amount of variation that you're expecting to see within the process. I would say that there really isn't a right or wrong way of determining how much data you collect. The key here is that you need to understand and be aware of how short-term data is less likely to have special causes reflected within it. At the same time, long-term data does have some of those special causes reflected in it. And it's more likely to see some shift within the short term. So you just have to be careful when you're working with your data. If you're collecting short-term data, you got to be careful to not use that data to predict what the performance of the process will be over the long term, because you're not including the special causes within your short-term data. At the same time, if you're using long-term data, you can't use that to exactly predict what's going to happen in the short term, because your long-term data has the special causes that you may not see in the short term. So when you're trying to evaluate between both, that's where you would either add or subtract 1.5 standard deviations to reflect that variation that you might see as you translate between short and long-term data. Again, we're going to get a lot more detail into this in the analyze phase when we explore a little more detail the process capability.
All right, before we close this lesson, let's discuss how we can apply some of these concepts in a practical way.
We'll try to identify at least 2 different metrics that you use in your organization, again, that are continuous values, and try to do the following things. First, determine what may represent short versus long-term data for each of those metrics. So as an example, how frequently is the metric data reported? If it's reported on a daily level, then it may just be a few weeks that could represent short-term, and a few months may represent long-term. However, if the data happens to be reported monthly, then maybe it will be a few months that represent the short term, and maybe a whole year or longer that would represent the long term. So just try to consider that as far as what each of your metrics represent, short versus long-term data. And then try to pull enough historical data for each metric to account for at least the long-term data. You want that for each of your metrics. So depending on how you're determining long-term data, use that at least as your guide for how far back you need to collect your historical data for this exercise. And for that data, calculate the mean and the standard deviation for all of the data across that entire long term. Then I want you to do is calculate the mean and standard deviation for only about 25% of the data across the short term. So as an example, if you only have 24 observations of weekly data, then break that into 4 different groups where you're calculating the mean and the standard deviation maybe for the first 6 observations. Then you're doing it again for the next 6 observations, and so on. Now, based off of all this that you've done, compare the results between each of the short-term sets of values and the long-term values. So how do the short-term values differ between each of those other short terms in the set? And also, how do those short-term values differ from the overall long-term values that you've seen? And which set of data appears to reflect the true mean and the true standard deviation for the overall process?
Well, that wraps up this lesson. Check out StatStuff.com for many more resources that can help you achieve powerful results. I'm Matt Hansen. Thanks for watching.